In this video, I'm going to go through the first review for the radicals and complex numbers unit. So for number one, the first three, we're just going to simplify some different radicals. So for A, I notice I have a 24 under the radical, an x to the 10th, and a y to the 15th. So I take this in three pieces. I start with the 24 and I ask myself, what numbers multiply to 24 where one of them's a perfect square? Now in this case it's just 4 and 6. If there were more perfect squares that divided into 24, you could try them out in your calculator, but you always want to pick the biggest perfect square so you don't have to simplify any further. Now, when my exponent is an even number for variables in a radical, I leave them, but when it's an odd number, my trick is that I break it up into 1 and then my leftovers. So if I take 1 away from 15, I'm left with 14, which is why I have a y to the 14th here. Now, the whole idea behind that is that once it's an even number, I could take it out of the radical. So radical 4 is just 2. Radical x to the 10th, well, I know if I multiply x to the 5th to itself, I'll get x to the 10th because I add those exponents. So my quick trick is I just take half of the exponent when it's even. So for y to the 14th, I'll skip that logic and I'll just cut 14 in half and get y to the 7th. So this is all what comes out of the radical. And inside I should still be left with a 6 and a y. So I have 4x cubed y, I'm just bringing down what was out in front, times 2 times x to the 5th, times y to the 7th, times radical 6y. And then I combine whatever I can on the outside. So 4 times 2 is 8, x to the 3rd times x to the 5th is x to the 8th, and y times y to the 7th is y to the 8th. For cube roots like b, all of the same sort of rules apply, but instead of thinking about perfect squares, you want to be thinking about perfect cubes. So remember that's something like 1, 8, 27, 64, 125, and so on. Right? 125 is 5 cubed, 64 is 4 cubed, and so on. So I'm going to break up 16 into negative 8 times 2. Now the whole reason why I choose negative 8 is because I know that a negative number under the cube root comes out as a negative number because negative 2 cubed is negative 8. So you could choose to leave the 2 as negative, but I always like to try to take the negative outside the radical. So for x to the 16th, I'm going to break that up into x to the 15th times x to the 1st, and I'm going to leave y to the 21st. Because remember the rule is we want the exponent for the variable to be divisible by 3, and that'll make it a perfect cube. So the cube root of negative 8 is negative 2. The cube root of x to the 15th is just x to the 5th. And the cube root of y to the 21st is y to the 7th. The whole reason behind that is that if I multiply y to the 7th to itself 3 times, I'll get y to the 21st. And that's what a cube root is asking us. What do we need to multiply 3 times to get what's under the radical? So, again, I'm going to bring those out. You don't have to show the step. I'm just showing it for sake of argument here. Times negative 2 times x to the 5th times y to the 7th. And I still have a 2 and an x under the radical. And when I end up multiplying everything out, I get negative 10, x to the 8th, y to the 11th, times radical, the cube root of 2x. So don't forget to keep writing that cube root down there. For c, you should notice that for a square root, there's no 3 here. It's kind of hard to think about having a negative under the radical, because that's asking you what number do you need to multiply to itself to get a negative. Well, I know a positive times a positive is equal to a positive, and a negative times a negative is equal to a positive. So, from this point, we haven't had any answer to this. But the whole idea is that we created a new number, I, such that when we multiply it to itself, we get a negative number, negative 1. So the whole trick here is to break up 200 into 200 times negative 1. And the reason that works out is because the square root of negative 1 is what we define I to be. So a quick trick to think about is that anytime you see a negative under the radical, you could pull it out as just I and then simplify as normal. So 200 I would just break into 100 times 2. Again, 4 divides into 200, but you're looking for the biggest perfect square. That's going to be 100. And the square root of 100 is 10. When you multiply that to your 1/2, you're left with 5i radical 2. So anytime you have a negative under the radical, you should have an I somewhere in your answer. Now we're going to perform some operations after we simplify. So notice your two radical expressions here are separated by a minus sign. So I'm going to try to simplify them first. I know the square root of x to the 4th, if I cut that exponent in half, it's x squared. So that first expression becomes 5x squared, and I still have a 3 left under the radical. And let me see if I can simplify this first. Well, I know 27 is the same thing as 9 times 3. And if I take the square root of 9, that's just 3. And if I take the square root of x to the 4th, that's just x squared. So really what I could do to save myself a little bit of time here is I could multiply the 3 to the 2 to get 6 and bring out the x squared to just have a radical 3 left over. Now remember your rules for combining radicals. You can only do it if you have the same expression under the radical and the same variable to the same exponent. So in this case we both have an x squared and a radical 3. So I can combine those coefficients. 5 minus 6 is -1. And leave the radical and the variable expression. Now for cube roots, all the same rules still apply. But in this case, it actually simplifies pretty nicely because the cube root of 8, well, 8's a perfect cube, so that's just 2. Plus 2 times, well, the cube root of 64. 64 is also a perfect cube. That's just 4. So this becomes 2 plus 2 times 4, which is just 8. So when you simplify, it's 10. Now, if you don't remember any of your perfect cubes, the good news is your calculator has a function to do that. If you hit the math button and arrow down to number 4, you'll see a cubed root. If you just type that in, it'll tell you if it simplifies or not. So if you're never sure if you have a perfect cube, always just test it out in your calculator to make sure it works. For C, I noticed that I'm going to be working with imaginary numbers because I have some negatives under the radical, so I'm going to pull those out first before I do anything. 48 can break down into 16 times 3. Plus 3.5, and 25 is a perfect square. Radical 25 is just 25. And I pulled out the I from the negative under the radical, and 27 we already saw that breaks down into 9 and 3. Again, I picked those numbers because one of them is a perfect square, so it'll simplify when I take it out of the radical. So what I'm left with here is 4i, radical 3. I can combine those because those both don't have radical terms with them, to 8.5. Minus 3i radical 3. Now I notice that my first and my last term both have imaginary parts to them, and they both have the same radical. So 4i rad 3 minus 3i rad 3 is just 1i rad 3, plus that 8.5 that I have hanging out. Now I always try to put my imaginary part at the end because usually they want me to leave it in a plus bi form, where that imaginary part comes after the real part that doesn't have the I. For D, I notice that I do have a negative under the radical and I have a perfect square. So this part would come out as I, and this part would come out as 4. So I could simplify radical -16 to just 4i. And again, you could type that into your calculator if you're not sure. Minus -2 plus, I have the same sort of thing here where 81's a perfect square, and I could bring that out as 9i. Remember, when you are subtracting complex numbers and you have parentheses, that you need to distribute that negative before you start combining your terms. So that becomes positive 2 minus 9i, and I add my real parts to get 5, and I add my imaginary parts to get -13i. Number 3. Express the product of 2 plus radical -9 and 3 minus radical -16 in the form a plus bi. So remember, product just means to multiply. And these are both complex numbers because I recognize that it has a real part and an imaginary part. So radical -9 we already saw simplifies to 3i, and radical -16 again simplifies to 4i. So if I'm multiplying these, this is going to be one of those double distribution problems, right? 2 times 3 is 6. 2 times minus 4i is minus 8i. 3i times 3 is 9i. Now here's where it gets a little tricky. 3i times that minus 4i. If you're multiplying those, you'd have to multiply the coefficients. 3 times negative 4 is negative 12. And you'd have to multiply those imaginary units too. I times I is I squared. So here you have a minus 12 I squared. So let's think about I squared for a minute. We already talked about how I is the same thing as radical negative 1. And when I square a radical, I know that gets rid of the radical. So when I square I, that's the same thing as if I just have negative 1. So if I try to simplify that a little bit here, this is minus 12 times negative 1, which just ends up being a positive 12. When I combine that with my 6 over here, those are my real parts. 12 plus 6 is 18. And minus 8i plus 9i is just 1i. So this is simplest a plus bi form. I've got my real part in the front and my imaginary part in the back. So let's try some more multiplying. For a, since they're both cube roots, I could just take what's under the radicals and multiply them and keep them under the radical. 4 times 4 is 16. And it says to multiply or divide and simplify completely. So I'm going to do that same trick where I think about what perfect cubes divide into 16. The only one that does nicely is 8, and when I take that out, it becomes just a 2. So my final simplified answer here is 2, the cube root of 2. For b, it's important to recognize that these look almost the same, 1 plus radical 5 and 1 minus radical 5, except that the sign in between them has changed. So remember, these are called conjugate pairs when that happens, and they end up simplifying pretty nicely. So let's see what happens. 1 times 1 is 1. 1 times negative radical 5 is negative radical 5. Radical 5 times 1 is positive radical 5. And radical 5 times a minus radical 5. Remember, if they're under the radicals, you keep them under the radicals when you multiply. So they multiply to radical 25. Now you should notice here that a minus radical 5 and a positive radical 5 just cancel to 0. So all you have left here is 1 minus radical 25, but even radical 25, that's a perfect square, so that just simplifies to 5. And all you have is negative 4 when you simplify. That will happen every time you multiply conjugate pairs. And if you weren't sure about that, you could actually just plug this whole expression right into your calculator to double check. Again, since they're both square roots, I'm going to just multiply everything under the radical. 3 times 8 is 24. X to the 5th times x to the 1st. Remember, I add those exponents. And y to the 1st times y to the 7th is y to the 8th. So 24, we've seen this number before. It breaks down into 4 and 6. And x to the 6th and y to the 8th are both perfect squares already because those exponents are even. The 4 comes out as a 2. When I take half of that exponent, it becomes x to the 3rd. And when I take half of that exponent, it becomes y to the 4th. So all I'm left with is 2x cubed y to the 4th on the outside and a 6 under my radical. For division, all of the same rules apply. You divide the outsides and you divide the insides. So in this case, I don't have anything on the outside, so I'm just going to divide 150 and 3 to get 50, and a to the 5th divided by a to get a to the 4th. 50 I recognize as a multiple of 25, so I break that down into 25 times 2, and I can take out the 25 as a 5 since that's a perfect square, and the a to the 4th as an a squared since that's a perfect square. So my final answer is 5a squared on the outside times radical 2. For e now, I do have stuff on the outside and stuff on the inside. However, it's important to recognize that there's a negative under the radical there, so I'm going to be working with some sort of imaginary number. So usually before I do anything here, I'm just going to pull that negative out to show that I have a negative number in the numerator. Once you do that, all of the same rules still apply. So I'm going to divide the 6 and the 3 to get 2, but there's still an I hanging out there. and I'm going to divide the insides 50 divided by 2 to get radical 25. Radical 25, again, I'm pretty happy about that because that's a perfect square. Simplifies to just 5. So my final answer when I multiply those coefficients is just 10i. Now when I'm multiplying two imaginary numbers, before I start multiplying the insides and the outsides, again, I just pull that I out to show that I'm working with imaginary numbers. The reason I do that is because I'm going to know that I'll have to multiply, they're linked by multiplication. I do that because I know I'm going to have to multiply I and I to get I squared, and I know I squared simplifies nicely. So I'm going to multiply these outsides here. 2i times 3i is 6i squared, and when I multiply the insides, 24 times 2 is 48. Remember from before, I squared just simplifies to negative 1, so my coefficient out here is just negative 6 when I multiply the two. 48 breaks down into 16 and 3, and I take the 16 out as a 4. So when I multiply the 4 to the negative 6, I'm left with negative 24 times radical 3. So even though you were multiplying two imaginary numbers here, all you were left with was a real number, because when you multiply the two imaginary, the I squared's reduced to negative 1. So just keep that in mind. Express the sum, remember that means to add, of 5 plus radical negative 36 and 3 minus radical negative 16 in a plus bi form. So I know both of these are complex numbers again because I have a negative under the radical there. So they want me to add 5 plus 6i and 3 minus 4i. So I'm going to combine like terms here. 5 plus 3 is 8, and 6 minus 4 is just 2. So my final answer in simplest a plus bi form is 8 plus 2i. Again, notice I put the real part first and the imaginary part in the back. Algebraically solve for x and justify the solution set. So remember, justify the solution set. That just means to check your answer to make sure that everything that you have works. Okay, for a, it gives me this exponent of 1/2, but remember that's just telling me that all of that's under a radical, right? A 1/2 exponent and a radical are the same thing. So in order to get rid of the square root here, I'm going to square both sides. So that gets rid of it on this side, and I'm just left with 2x plus 15, and I'm left with x squared on my right-hand side. Now, I notice this is a quadratic equation here because I have that x squared, and I usually want to try to get these equal to 0. However, it's always easier if your x squared term is positive, so I'm going to move this 2x over and the 15, rather than moving the x squared to the other side. So 0 equals x squared minus 2x minus 15, and now this looks like a regular trinomial where I just ask myself what adds to the middle term and multiplies to the last term. So as I'm going to factor this, I'm thinking about factors of negative 15 that add to negative 2, and you could try a couple out in your calculator, but it ends up being negative 5 and positive 3. So remember, this is an equation, so we need to keep going. I'm going to apply that 0 property to set both of my factors equal to 0 to finally get x equals positive 5 as one of my solutions, and x equals negative 3 as my other solution. But remember, it said to justify the solution set, so just to make sure, I'm going to plug this back into the original equation to make sure it works. So when I plug back in 5, my equation looks something like this. 2 times 5 is 10, plus 25 is, or plus 15 is 25, and radical 25 is just 5. So that one checks out. But when I try to plug in negative 3, something a little weird happens. So even from this step, some red flags should be going off, because if you have a radical expression that's equal to a negative, we know that we always get positive numbers out of a radical, so there's no way this equation can be true to begin with. When I simplify what's under there, negative 6 plus 15 is just positive 9, and the square root of 9 is just 3, which does not equal negative 3. So I need to go back to my solution set and actually reject that negative 3 because it causes something like this to happen. So that's actually an extraneous solution, and your only solution here is x equals 5. 9 times out of 10, when you have a quadratic and you solve it here for these radical equations, usually both of these solutions don't work, so just make sure to go back and check. For something like b, where you have two radicals, the whole idea is that you want to isolate both of them. So I'm going to move that radical x plus 4 to the other side, to be left with radical 2x plus 2 is equal to radical x plus 4. Now the reason I'm doing this is because when I square both sides, I want to be able to get those radicals to cancel. If I try to do it here in my first step, they're linked by subtraction, and that usually messes things up. Remember, this is just like I had a minus b, and I'm squaring that. That's not that I get rid of a and get rid of b, it's that I have to double distribute it, and that would be a real pain for this problem. So once I have both the radicals isolated, I square both sides, and I'm left with 2x plus 2 is equal to x plus 4. Now this is just a regular linear equation because I don't see an x squared anywhere. When I end up solving it, I subtract x on both sides here. I subtract 2. You could do this in 2 steps. I'm just doing it in 1. And I get x equals positive 2. But again, it says to justify the solution set, so I'm going to plug it in just to make sure it works. And it does. Now for cube root problems, most of the same rules apply. You want to try to isolate that cube root first, so I'm going to divide out the 2 here to get the cube root of x minus 3 equals 2. And you didn't have to. You could do this step that I'm going to do here first. But I always think it's easier if I have the radical isolated. Now, to get rid of a square root, we squared both sides. To get rid of a cube root, I'm going to cube both sides. So that cancels here. I'm left with x minus 3. And 2 cubed is just 8. When I add 3 to both sides, I'm left with x equals 11. And again, when you plug it back in, it works out. Now for the last equation, this combines both imaginary numbers and square root equations, but I'm still going to apply those same rules where I first want to isolate the radical, and I can combine those like terms because they're both imaginary, and I'm going to square both sides because that gets rid of the radical here. So I'm left with 5 minus 2x, and then think about what 3i squared would be. Well, 3 times 3 is 9, I times I is I squared, and I squared is just negative 1, so 3i squared would just simplify to negative 9. And your calculator's smart enough that you could plug this straight into your calculator, 3i squared, and it would spit out negative 9 if you weren't sure. When I finish solving this, I subtract 5 on both sides. I get negative 2x equals negative 14, and when I divide out that negative 2, I get x equals positive 7. And again, you should always plug that back in to check, and when I do here, something interesting happens. 5 minus 2 times 7 plus 2i, 5i, and 5 minus 14 is negative 9 plus 2i equals 5i, and negative 9 under the radical just simplifies to 3i. So 3i plus 2i is in fact 5i, and again it checks out. Below is the student's work solving the equation 2 times radical 3x plus 3 equals 12. What mistake did the student make? What is the correct solution? Okay, so it looks like right from the get-go he forgot to isolate the radical. So when he squared both sides of the equation, he didn't square everything. So this is the problem step right here. So he has 2 ways he could have fixed that. He could instead actually square all of both sides of the equation to get 4 times radical 3x plus 3 on this side. Or he could have divided out the 2 first to have that radical isolated. So we already divided out the 2. I'm going to try just squaring both sides from the get-go and seeing what happens here. So 2 times 2 is 4. Radical 3x plus 3 times radical 3x plus 3. It's just radical, or just 3x plus 3. The radical cancels. 12 squared is 144. I can distribute the 4 into my parentheses here to be left with 12x plus 12. And when I subtract 12 on both sides and divide by 12, I'm left with x equals 11. And you'll have to take my word for it. For this one, when you plug it back in, it does in fact check. For the last one here, it asks you to multiply out this complex number. It says the complex number c plus di is equal to this. What's the value of c? So it's pretty much just asking for the real part there. Now, if I were to square this, that means to multiply it out twice. Now, we already did one of these multiplication problems where we multiply 2 times 2, 2 times I, and so on and so forth. Now, notice that there's no variables here, and your calculator is actually pretty good at working with complex numbers when there are no variables. So if you hit the mode button, your calculator should always be in A plus BI mode, so I'm just going to turn that on right here. And from there, I'm going to go back to my home screen, and I'm going to just type this in, 2 plus I squared. Open parenthesis, 2 plus your I button. If you hit second period, that'll get you your I. I'm going to close the parentheses, and I'm going to square it. And it tells me it simplifies to 3 plus 4i. And if you were to do all the distribution out, you'll see that that is in fact true. And the question is just asking me what is the value of c. So that's the real part, and the value of c is just 3 there. Now, the good news is your calculator is pretty good at working with all different sorts of imaginary and complex numbers. If for some reason you're working with higher powers of I, though, let's say you're trying to do I to the 55th and seeing what that simplifies to, depending on how updated your calculator is, if you have one of the color ones, it'll work. But for these older ones, it doesn't quite know what to do with that. So if you hit the math button, arrow over to number, and go down to number 3, I part, your calculator will know you're working with different powers of I, and when you go to enter it, it will be able to simplify it a lot nicer. So that's just something to keep in mind. Even for the last multiplication problem we did, where was it? This one right here, where it says to express the product, we could have typed that straight into the calculator from the get-go because there are no variables, and it would have spit out 18 plus I as well. So that's one quick way to check yourself for these multiplication problems. Express in simplest A plus BI form. So, you could go through all the hassle of simplifying these. Remember we talked about those I values. It's either I is equal to I squared is equal to -1. If I multiply by another I end up at -I. And if I multiply by another I, so -I times I would just give me +1. You could memorize those facts, and I think it's good to know them, but again, your calculator is pretty savvy when it comes to these higher powers of I. So rather than trying to simplify this, for a couple of these examples, I'm just going to show you how I would approach them since there are no variables here. So when I type that whole thing into my calculator, it tells me it simplifies just to -I. So since there were no variables here, that was the easiest bet for me. And that's going to be the easiest way to approach all of these for 9, so I'm not even going to show them here.